Good morning, students. Now we move on to an expression for force per length between the two parallel infinitely long current carrying conductors. Force per length between the two infinitely long current carrying conductor. This is one straight conductor which is infinitely long. I call it as X. Another parallel infinitely long straight conductor, I call it as Y. Both of these parallel conductors, straight conductors, infinitely long, carries current. For example, current in first one, let it be I1, and current in the second, let it be I2. These are the two infinitely long, straight, parallel current carrying conductor where current in both are in the same direction. We have one more case where current is flowing in the opposite direction. One is upwards and there is downwards. These two conductors are separated by a distance d. We need to calculate what is the expression for force between the two. Since it is infinitely long, so we get an expression for force per length. So force per length between two parallel straight current carrying conductor. Expression for force per length between the two straight parallel current carrying conductor. Between them, what force is there? In the first place, we have studied, if there is a mass m1, there is one more mass m2, between the two there is a gravitational force. Why there is a gravitational force? See, this is a mass m1, surrounding there is a magnetic field. Space surrounding the mass is called gravitational field. So not magnetic field, gravitational field. Surrounding this mass there is a gravitational field. Surrounding this mass there is one more gravitational field. The two fields interact. Because of the interaction of the two fields there is a force, and that is called gravitational force. And we know the formula, F is equal to G into m1 m2 by r square. Similarly, there is a charge, electric charge Q1, one more electric charge Q2, point electric charges, static charges. Between them there is an electric force. You have studied in your second PU topic. Why? Surrounding this electric charge there is an electric field. Surrounding this also there is one more electric field. The two electric fields interact. Mass surrounding there is a gravitational field. Surrounding the charge, electric charge, there is an electric field. So interaction of the two gravitational field will exert a gravitational force. Interaction of two electric field will exert electric force. Similarly, those are the two current carrying conductors. These are the two current carrying conductors. Surrounding the current carrying conductors, there is a magnetic field. There is a magnetic field surrounding this, there is a magnetic field surrounding this. Because of these two magnetic field, interaction of these two magnetic field, there is a force, and that is called magnetic force. So just like between the two mass, there is a gravitational force. Between two electric charge, there is a electric force. Similarly, between the two current carrying conductor, there is a magnetic force. So we need to calculate the expression for the force between the two current carrying straight conductors. Now how to find this expression? First we need to calculate the magnetic field. Surrounding this there is a magnetic field. Surrounding the straight current carrying conductor there is a magnetic field. If you want to find the magnetic field somewhere here, there is a magnetic field here because of this wire, there is a magnetic field here because of this wire. And already we have studied the expression for magnetic field. Due to infinitely long straight conductor, this is the wire which is very long, which carries current I. If you want to find the magnetic field at any point at distance d, the formula B is equal to mu naught by 4 pi into 2I by d. Expression for magnetic field at any point due to infinitely long straight conductor which carries current. Where what is mu naught by 4 pi? Mu naught by 4 pi is 10 to the power of minus 7. I, current flowing through the conductor, and d is the distance from the conductor to the point where you are measuring the magnetic field. Is it right? Therefore, you can measure the magnetic field here. This is a place which is surrounding this wire. Therefore, here we have magnetic field at this wire. This is also a point surrounding this conductor, because this is the place surrounding the second conductor also. Therefore, here we have magnetic field due to second wire. So here we have magnetic field due to both wire. Here also we have magnetic field due to both wire. Here also we have magnetic field due to this both wires. How to find the magnetic field? Use the formula. And magnetic field is a vector quantity. Use the formula, find the magnitudes, and the direction of the magnetic field is measured using right hand clasp rule. That also you have studied. What the right hand clasp rule say? Imagine a current carrying conductor is clasped with right hand. Thumb shows the direction of the current. Then other finger encircle will give the direction of the magnetic field. Right hand is clasped such that thumb shows the direction of the current. Then other finger encircle will give the direction of the magnetic field. Therefore, if the current going is up, you clasp it like this. This is the direction of the magnetic field. So here it is inwards, here it is outwards. What is the direction of the magnetic field due to this wire? Again you hold it like this. This is the direction. Here it is inwards, here it is outwards. So magnetic field here because of this wire, magnetic field here because of this wire, both are towards the observer from the backboard coming out. So you can add it. What is the magnetic field here? Magnetic field direction here because of this wire. You can hold it like this. So it is inwards. Because of this also it is inwards. So you can add it. How to find the magnetic field? Somewhere in between. Now it is opposite. Because magnetic field here, because of this wire, the wire X is, just see here, this is coming out and here it is going in. So inwards. What is the magnetic field here? Because of the wire Y, right hand clasp rule. Here it is going in and here it is coming out. Therefore, magnetic field here because of this wire is inwards. Magnetic field here because of this wire is outwards. So find the magnitude and then subtract because there is the opposite direction. Therefore, what I am saying is any place, maybe here or here or here, anywhere, either on the right or on the left or anywhere in between, you can find out the magnetic field to both wire. Now my question is, find the magnetic field on the wire. Listen carefully. What is the magnetic field on the wire? I need to calculate the magnetic field at this point. On this point, there is a magnetic field only due to X and not due to Y. Because whenever there is a wire which carry current, there is a wire which carries current. What is the formula to measure the magnetic field, which is the basic formula? It is Laplace law. If there is a current element I which carry current I whose length is dl, then magnetic field at any point is given by the formula mu naught by 4 pi into ideal sine theta by r square. This is the basic formula to measure the magnitude of the magnetic field. And in this formula, and what is theta? Theta is the angle between current element. This is the wire which carry current which is very very small, whose length is dl. And what is theta? Angle between current element and line joining point and the current element. This is theta. In this formula, if you put theta is equal to 0, sine 0 is 0, the magnetic field becomes 0. Theta 0 means what? Theta 0 means you are taking this point somewhere along the line. That means if this is a wire which carry current, and if you are finding the magnetic field along that wire, along the conductor, the magnetic field is 0. So what is the meaning of this? If there is a straight current carrying conductor, and that straight current carrying conductor will produce magnetic field only in the surrounding region and not on the wire. Therefore, this is the place on the conductor Y. At this place, listen carefully, at this place on the conductor Y, there is no magnetic field due to I2, but there is a magnetic field due to I1. Is it right? So at this point, there is no magnetic field due to I2 or Y wire. But this is surrounding conductor X. Therefore, there is a magnetic field due to X. That means carry current I1. Clear? So this is a straight conductor. I call it as X. Straight conductor, I call it as Y. This carries current I1, this carry current I2, separated by a distance D. So first job is what? Finding the magnetic field on Y. So magnetic field on Y due to I1, that is due to X, and X carries what current? I1. I call it as B1. I call it as B1. So what is B1? B1 is a magnetic field on this wire, and the magnetic field on this wire is not due to the current I2, it is due to the current I1. And what is the formula? Formula I already told you, it is mu naught by 4 pi 2I1 by D. What is I1? I1 is a current and D is a distance. So this is an expression for magnetic field on this wire due to this current carrying conductor. Find out the magnetic direction of the magnetic field. You are finding the direction of the magnetic field here, and that magnetic field due to this current, apply right hand clasp rule. This is the right hand clasp rule. Current is going vertically upwards. Therefore, this is the direction of the magnetic field. Here it is coming outwards and here it is going inwards. See carefully. This is the direction of the magnetic field. Here it is coming outward and here it is going inward. So I represent like this. So this is the direction of the magnetic field. So inwards. What it is? Inwards. Now, this is a current carrying conductor. Carry current I2. The place where this conductor is present, there is a magnetic field B1. And we have one theory. Current carrying conductor, when it is kept in the magnetic field, experiences a force. Already we have studied in the previous class. Current carrying conductor kept in the magnetic field. That means if there is a magnetic field B, and in that magnetic field, I keep one wire which carry current I. So two magnetic fields came there. One magnetic field already present, which is B. This is a wire which carry current I, and surrounding this there is one more magnetic field came. So whenever the two magnetic field is there, there is a force. So this is a magnetic field. In the magnetic field, there is a current carrying conductor is placed. So when a current carrying conductor is kept in the magnetic field, it experiences what? Force. And what is the formula for force? F is equal to BIL sin theta. Already studied in the previous classes. Where what is B? Magnetic field. I, current carrying, the current which is going in the conductor. What is L? Length of the conductor. And what is theta? Theta is the angle between magnetic field and the current element. Current element is same as that of the direction of the current you take. Is it right? So applying this formula, in this case, this is a wire which carry current I2. And this conductor which carry current is kept where? In the magnetic field B1. So current carrying conductor kept in the magnetic field experience force. So force on whom? Force on Y. I call it as F. and that is given by the formula B. What is B here? B1 into I. What is the current going? I2 into L into sine theta. What is theta? Theta is the angle between magnetic field and the current. What is the direction of the current here? Here the current is vertically up. This is the direction of the current, and this is the direction of magnetic field. I told you magnetic field is inwards. So this is the direction of magnetic field. There is the direction of current. So what is the angle? Angle is 90 degree. So substitute theta is 90 degrees, sine 90 is 1. But here what is L? L is a length, it is infinitely long. Therefore we can write the force per length is given by the formula. I am bringing this L here. So force per length is given by the formula B1. What is B1? Mu naught by 4 pi 2 I1 by D. Mu naught by 4 pi 2 I1 by D is B1 into I2. L has come to the denominator on the other side. Sin theta, theta is 90 degrees, sin 90 is 1. So this is an expression. This is an expression for what? Force per length between the two parallel current carrying straight conductor. This is the formula for force on the wire Y. Force on the wire Y. What is the direction of the force? Direction of the force is given by Fleming's left hand rule. That also you have studied in the previous class. Fleming's left hand rule. What the Fleming's left hand rule say? Stretch first 3 fingers of the left hand mutually perpendicular to each other. 4 fingers show the direction of the magnetic field. First one. 4 fingers show the direction of magnetic field. Always stretch 1 finger first. 4 fingers show the direction of magnetic field. Fix it. Middle finger show the direction of the current. Middle finger also fixed. Then thumb show the direction of the force. 4 fingers show the direction of magnetic field. Middle finger show the direction of current. Then thumb show the direction of force. Don't stretch all the 3 fingers together. Then you will get confused. So stretch one by one. So here 4 fingers show the direction of magnetic field. This is the direction of the magnetic field. Magnetic field is inwards. Middle finger show the direction of current. Current is upwards. Now you turn it like this. You see here? I am turning. 4 fingers show the direction of magnetic field. Middle finger show the direction of current. Now stretch the thumb. Thumb show the direction of force. So this is the direction of the force. And what is the direction of force? It will be towards X. We have calculated force on whom? Force on Y towards X. That means Y is attracted towards X. So towards X. That means conductor Y is attracted towards X. Understood? Okay. Now we will verify the second one. Vice versa. This is a conductor. Conductor is X. Current is flowing in it, and what is the value of current? I1, and the current is flowing upwards. In this place or on the conductor, is there any magnetic field? Yes. There is no magnetic field here because of I1. Because on the conductor there is no magnetic field. On the conductor, listen carefully, on the conductor there is no magnetic field to I1. But there is a magnetic field to I2, because for I2 this is surrounding. So what is the magnetic field on X? Magnetic field on X. Magnetic field on X, not due to I1 but due to I2. Due to I2, I call it as a B2. What is the formula? Magnetic field at any point due to a straight wire is given by the formula B is equal to mu naught by 4 pi 2. Which current? I2. I2 divided by distance D. This is what? Magnetic field here on the wire X. Due to which current? Not due to I1 but due to I2. Direction. Direction of the magnetic field. Right hand clasp rule. Don't confuse with these things. Finding the magnetic field, right hand clasp rule. Force on current carrying conductor, Fleming's left hand rule. So we are finding the magnetic field here. Don't hold the finger like this. We are finding the magnetic field here because of which current? I2. Therefore hold it here. This is the place which is on the left side. So tell me the direction how it is. It is coming like this. Here it is going inwards and here it is coming outwards. Correct, no? See? Right hand clasp. This is the direction. Here it is going inwards. Here it is coming outwards. So outwards. Outwards. This is outwards. So magnetic field on X. Magnetic field on X due to I2. It is mu naught by 4 pi to I2 by D outward. So this is B2. Why I call it as B2? This is the wire which carry current I1. And here the magnetic field is called B2 because it is due to the current I2. Now again come to the theory. Current carrying conductor kept in the magnetic field. Current carrying conductor kept in the magnetic field experiences force. What is the force on X? Force on X. Formula same. F is equal to BIL sin theta. BIL sin theta. Here which is B2. It is a B2. Current I1. L length, it is infinite long, therefore L can take here. Sin theta, what is theta? Theta is angle here, the magnetic field is towards you. It is outwards. Current is going vertically up. So what is the angle? It is 90 degree. So sin 90, 1. Therefore F by L is equal to, what is B2? Mu naught by 4 pi 2 I2 by D, 2 I2 by D. This is B2. What is B2? Mu naught by 4 pi 2 I2 by D. Mu naught by 4 pi 2 I2 by D, it's B2 into I1 into I1. Length is kept on the left side. Sin theta, sin 90 is 1. So this is the force per length. Force per length. So force per length acting on Y, acting on X, we got it both same. It is I2, same. Force per length is given by the formula mu naught by 4 pi to I1 I2 by D, mu naught by 4 pi to I1 I2 by D. That means force acting on both are same. Direction, Fleming's left hand rule. What the Fleming's left hand rule say? 4 fingers show the direction of the magnetic fields here. Magnetic field is coming out, see like this. 4 fingers show the direction of magnetic field. Current is going vertically up, see like up. Is it right? Magnetic field is towards the observer. This is the magnetic field. Current is going vertically up. Then see the force direction. It is towards the right for you. Towards right means it is towards Y. Towards Y. So what you understood from this? Force acting on Y is towards X. Force acting on X towards Y. That means Y is attracted by X and X is attracted by Y. We know force always occur in pair. Newton's third law. And for every action there is an equal and opposite reaction. So both forces are equal, both forces are opposite. Yes, you can see here, it's proves. Both forces are equal. Conductor X is attracting conductor Y and conductor Y is attracting conductor X. Both force same. And X is attracting Y towards it. Y is attracting S towards it. So one force to the left, another force to the right. So this is an expression for force per length between the two parallel, infinitely long, straight current carrying conductors. And what is the expression for the force per length? F by L is equal to mu naught by 4 pi into 2 I1 I2 by D. Is it right? Okay. Next is, we want to, the force per length, if the currents are flowing in the opposite direction. Derivations I won't repeat it, I'll just see the directions, that's all. Because derivation part, each and everything is same as that of the previous. Every term, only direction differs. Therefore, I will show only the direction. This is one wire, infinitely long, X. Another wire, infinitely long, Y. This is carrying current I1 vertically up. This is carrying current I2 vertically down. See, earlier I took two conductors where current both flows in the upward direction, same direction. Here they are opposite direction. There it is a parallel, here it is anti-parallel. Separated by a distance d. I told you derivations is same as that of the previous one, only direction differs. So consider two parallel conductors, X and Y, carry current I1 and I2 in two opposite directions. And the two conductors are separated by a distance d. I need to calculate the force per length between them. To start with, finding the magnetic field here. What is the formula for magnetic field? I am not ready. What is the formula for magnetic field here? Magnetic field here, it is not due to current I2, it is due to current I1. And what is the formula? B is equal to mu naught by 4 pi to I1 by d. Direction. Magnetic field here because of this wire, where the current is going vertically up, right hand clasp rule. This is the direction of the magnetic field lines. So here it is coming out and here it is going in. Perfect, no? This is the wire which carry current I1. Surrounding magnetic field is produced. So applying right hand clasp rule. Say, here it is coming out and here it is going in. So this is the direction of the magnetic field. I call it as B1. Why it is B1? Because it is a magnetic field due to I1. Now the theory, current carrying conductor, carrying current I2, kept in the magnetic field, B1 experiences a force. F is equal to BAL sin theta, all those things are there. Same formula you will get to. Direction, applying Fleming's left hand rule. Forefinger show the direction of magnetic field, middle finger show the direction of current, thumb show the direction of force. Don't stretch all the three fingers together, I told you one by one. Forefinger show the direction of magnetic field inwards. Forefinger show the direction of magnetic field. Middle finger show the direction of current. Here it is coming down. First always fix one finger, then middle finger is stretched and change the direction. One finger you have to fix first, then you fix the second one, then stretch the third one. So forefinger show the direction of magnetic field, fix, don't change it. Middle finger show the direction of current, see current is coming downwards. So forefinger show the direction of magnetic field, middle finger show the direction of current, thumb show, now stretch thumb show the direction of force, yes. Therefore force will be, this is the force. So what is the direction of the force? Force on Y, away from X. That means the conductor Y is repelled because of the X. Previous case, conductor Y was attracted, now it is repelled. Y gets repelled because of X. Now you see for X, this is a wire, carry current, direction of the current is upwards. Current is I1. Here, is there any magnetic field? Yes. Here there is no magnetic field due to I1, but here there is a magnetic field due to I2. How to find the direction of the magnetic field here? Applying right hand clasp rule. Finding the magnetic field here, but current due to that current. Therefore, there you have to hold. Here the current is not going up, the current is coming downwards. This is the direction of current. See it carefully. This is the direction of current. So see the encircled fingers. So here it is coming out, here it is going in, here it is coming out, here it is going in. So this is the direction of the magnetic field. And I call this magnetic field as B2. Why? Because this is the magnetic field to which current? I2. Clear? So this is a wire which carry current. Current is upwards, I1. Here there is a magnetic field due to the current, I2, and that magnetic field is inwards. Now come to the theory. Current carrying conductor kept in the magnetic field experience force. Fleming's left hand rule. 4 fingers show the direction of magnetic field, inwards. Middle finger show the direction of current. Current is upwards. 4 fingers show the direction of magnetic field, inwards. Middle finger show the direction of current, upwards. Thumb show the direction of force. You can see the left, therefore this is the direction of force. This is the force on whom? Force on X, which is away from Y. So what is happening here? Conductor X is pushed away from Y. Conductor Y is pushed away from X. Both are equal and opposite. And what is the formula? It is force per length is equal to mu naught by 4 pi 2 I1 I2 by D. So two parallel infinitely long straight current carrying conductor. The force per length is given by the formula mu naught by 4 pi 2 I1 I2 by D. What is I1? I1 is the current, I2 is the current on another conductor, D is the distance between the two conductors. And what is the type of force? If the current flows in the same direction, if the current flows in the same direction, the force is attractive. X is pulled towards Y, Y is pulled towards X. If the two currents flow in the opposite direction, it is repulsive. X is pulled away from Y, Y is pulled away from X. The two conductors go away. Same current direction towards, opposite away. So if the current is parallel current, we say same direction means parallel. Attractive force. Anti-parallel means opposite. It is repulsive force. And this is an expression for the force. Is it right? Therefore, both case, the derivation part is same. Only the direction part is different, and that I explained with the picture, figure. Is it right? Now with the help of this, we can define the unit current. This is similar to that of defining unit charge from Coulomb's inverse square law. But I remembered, there is one charge Q1, another charge Q2, separated by distance D. What is the Coulomb force between them? Electric force. 1 by 4 pi epsilon naught into Q1 Q2 by D square. Remember, this is the Coulomb's inverse square law. There is one charge Q1, another charge Q2, point static charge. Between them there is an electric force, and this is the formula for electric force. Using this formula, we have defined the unit charge, that is 1 Coulomb. Remember how we defined? When Q1 is equal to 1, Q2 is equal to 1, D is equal to 1, then F is equal to 1 by 4 pi epsilon naught, that is 9 into 10 to the power of 9. So that is the definition of unit charge. Unit charge is that charge which when kept at a distance of 1 meter from an identical charge in air repelled with the force of 9 into 10 to the power of 9 Newton. Same concept here. You define the unit current. What is the unit of current? 1 ampere. Always we defined it. I is equal to Q by T. I is equal to Q by T. 1 Coulomb means 1 ampere means 1 Coulomb of charge flows in 1 second. 1 Coulomb charge flow through a conductor in 1 second, and the current is said to be 1 ampere. This is also the way by which you can define 1 ampere. And there is a common question which is asked for 5 marks. Derive an expression for derive an expression for force per length between the two parallel current carrying conductor, hence define 1 ampere. 4 marks for the definition, 4 marks for the derivation and 1 mark for the definition. So how you define 1 ampere? I1 is equal to, I2 is equal to 1 ampere. I1 is equal to, I2 is equal to 1 ampere. D is equal to 1 meter. When I1 is 1, I2 is 1, D is 1. Then what is force per length? Mu naught by 4 pi. What is the value of mu naught by 4 pi? 10 to the power of minus 7 into 2 is there. So 2 into 10 to the power of minus 7. So how you define 1 ampere current? So 1 ampere is that current. 1 ampere is that current. So this is a wire which carries a current of 1 ampere. This is another wire which carries a current 1 ampere. And this is separated by distance 1 meter in air. So how do you define? 1 ampere is that current which when flows through two parallel conductors. Here also 1 ampere, here also 1 ampere. So 1 ampere is that current which when flows through two parallel conductors separated by a distance 1 meter in air. Separated by a distance 1 meter in air, exerted by the force of 2 into 10 to the power of minus 7 Newton per meter. It is a force per unit length. Exerted with the force of 2 into 10 to the power of minus 7 Newton per meter. So this is how we define 1 ampere. So what is 1 ampere? 1 ampere is that current which flows through two parallel conductors separated by a distance of 1 meter in air, repelled with the force of, if it is same current direction attracted, opposite means repulsion. Sorry, same means attraction, opposite means repulsion. So exerted is the best. So 1 ampere is that current which when flows through the two parallel conductors separated by a distance of 1 meter in air, experiences the force of, don't say attraction or repulsion, experiences a force of 2 into 10 to the power of minus 7 Newton per meter. Newton per meter. So this is about the expression for force per length between the two infinitely long straight parallel conductors, defining 1 ampere. Is it right? Next is moving on to the torque on rectangular current carrying coil kept in the magnetic field. Torque on a current carrying coil. Current carrying coil kept in a magnetic field. Torque on a current carrying coil kept in a magnetic field. We are taking a coil and this coil is kept in the magnetic field. See, this is the coil. Inside it is hollow, just only the outlines. I have taken the plank. Inside it is hollow, only the extreme parts. So imagine a rectangular coil. And in this coil, we are passing current. Assume that current is going maybe clockwise or anti-clockwise. And this current carrying coil, you keep in the magnetic field. For example, this is the direction of the magnetic field. This is the direction of magnetic field. For me, towards my left. That means for you, right. For you, the direction of the magnetic field is right. And this is the direction of the magnetic field. This is a coil which carry current, and this coil is placed. If the coil is placed like this, the angle between coil, listen carefully, angle between coil and the magnetic field is 0 degree. When I turn it 1 degree, 2 degree, 3 degree, 4 degree, and if you keep like this, what is the angle between magnetic field and the coil? It is 90 degree. This is a magnetic field, this is the coil. It is kept exactly 90 degree. What I do is, I keep in some arbitrary angle. That means, this is the direction of the magnetic field. I am going to keep the coil like this. If you keep like this, 90 degree. If you keep like this, 0 degree. Now 0 degree is the angle between magnetic field, and this scale is the direction of magnetic field. This is the coil. So here the angle between magnetic field and the coil is 0 degree. This is 90 degree. I keep in some arbitrary angle so that I will get a general expression. General expression. So this is how the coil is placed. Slant. Pictorially I can show like this. So this is the placement of the coil. Slant. Coil P, Q, R, S. Consider a rectangular coil. Listen here. This is a P, Q, R, S. This is P part. P, Q, R, S. P, Q is the front part. Imagine. Easy for you to understand. This is P, Q, R, S. This is length is maybe L. I'll write here, make a note here, that PS, let it be L, PQ, maybe B, length is L, breadth is B, PS is L, PQ is B. A rectangular coil which has got many number of turns. Imagine it is not one coil, many turns are there. Let the number of turns be N. How many number of turns? N number of turns. And this coil carries a current. When this coil current is flowing, assume that the direction of the current is like this. This is the direction of current. Okay. That means if you take this part as PQ, see here in the picture and this part as PQ, here PQ, see here PQ, here the current is coming down. Here it is going away from you. Here it is going up. Here it is coming towards you. Down, away, up, towards. Understand? So it is coming down, it is away, up and towards. This part is towards you, facing you. So consider one rectangular coil whose length is L, breadth is B, carrying having n number of turns, carry current I. Carry current I. Now this coil is placed. Where is coil is placed? This coil is placed in a magnetic field. This is the direction of the magnetic field for you towards the right. For the observer towards the right. This is the direction of the magnetic field. I will show the direction of the magnetic field on 4 places. This is the direction of the magnetic field. Magnetic field direction. And what is magnetic field? It is B. Instead of writing everywhere, I just wrote here. So consider one rectangular coil whose length is L, breadth is B, having n number of turns, carry current I, kept in the magnetic field B, making an angle. If the coil is kept like this, what is the angle? 90 degree. If the coil is kept like this, what is the angle? 0 degree. But I am keeping the coil somewhere like this, arbitrary angle. Less than 90, more than 0. It is somewhere here. Understood? This angle, let it be alpha. So this angle, I can show it here. This angle is alpha. Here also I can show. This is the place you can't represent. Is it right? So angle between magnetic field and the coil is alpha. It is slant. We need to get a general expression. General expression for what? Torque. We will see what happens. So basics you understood, no? So consider a rectangular coil. Length is L, breadth B, number of turns N, carry current I, kept in the magnetic field with the angle alpha. So what is alpha here? Alpha is the angle between magnetic field and the plane of the coil. Alpha is the angle between magnetic field and the plane of the coil. Now we have a theory, previous theory. What theory says? Current carrying conductor kept in the magnetic field experience force. Current carrying conductor kept in the magnetic field experience force, and the direction of the force is given by Fleming's left hand rule. Magnitude of the force is given by F is equal to BAL sin theta. You know. So this coil, we have 4 parts: PQ, QR, RS, SP. You will see individually. PQ is a conductor which carries current kept in the magnetic field. We will see what is the force. QR is one more part. We will see what is the force. Like that we will see the force on 4 different parts. Force on PQ, force on QR, force on RS, force on SP. So these are the 4 parts of the coil, and in all parts current is flowing and the coil is kept in the magnetic field. So current carrying conductor kept in magnetic field experiences force. One by one. Force on PQ. Force on PQ. What is the formula? BIL sin theta. What is the current here? Magnetic field, it is B. I already told. Everywhere magnetic field same. What is the current going in this wire? It is I. So B into I into B into I into L. BIL sin theta. What is theta? Don't say that it is alpha. Alpha is the angle between magnetic field and the coil, full coil. This is the coil, this is the magnetic field. That angle is alpha. Now we are not talking about the total coil, we are taking only this part. In this part, current is coming vertically down. So this is the direction of the current. You can see, you know, this is the coil, this is the direction of the PQ. Here the current is coming vertically down, PQ. And this is the direction of the magnetic field. What is the angle between these 2 pens? It is 90 degree. Perfect, no? Current carrying conductor, this wire is vertically down, and this is the magnetic field, and this angle is 90 degree. Therefore, what is sin 90? Sin 90 is 1. Sin 90 is 1. Therefore, what is the force on PQ? BIL. But I told there are n number of turns. Therefore, this is not one wire. There are n wires. So, it is into n. So, NBL. Therefore, force on PQ is NBIL. Direction of the force. Fleming's left hand rule. What the Fleming's left hand rule say? 4 fingers show the direction of magnetic field. 4 fingers show the direction of magnetic field. Middle finger show the direction of current. Here the current is coming down. Then thumb show the direction of force. It is towards the observer, towards you. So this is the direction. That means if I am keeping the coil like this, here the current is going vertically down. Magnetic field like this. This is the direction of the force. Current is going vertically down. This is the direction of magnetic field. This is the force. So force is towards the observer, towards you. Force on PQ, NBIL towards you. Force on QR. Force on QR. QR part you take. This is the QR part. First PQ part is this. QR part is this. Clear now? This is the QR part. See here. And this is the magnetic field direction. An angle between the scale and the pen is exactly alpha. You can see here, it is alpha. It is alpha. This is the magnetic field. This is the current direction or in conductor direction, and that is alpha. What is the force formula? It is n number of turns are there as it is. By L sin theta, n into B, magnetic field is B only, current is I, length, the breadth of this, what is the breadth? I told it is B, 1B, IB into sin alpha. Perfect, no? This is not 90 degree, alpha. So force on QR is NB, IB. Direction. Here also I can apply the Fleming's left hand rule. What the Fleming's left hand rule say? Four fingers show the direction of magnetic field, middle finger show the direction of current, thumb show the direction of force when they are mutually perpendicular. But the law can be little bit altered. It is not necessary that the magnetic field and the conductor has to be 90 degree. Even if the angle is less than 90 degree, the law can be applied. Four fingers show the direction of magnetic field. For example, this is the direction of magnetic field. This is the direction of the magnetic field. If the current is flowing in this direction, this is the force. This is magnetic field. This is the current carrying conductor. Force is up. For example, if the conductor carry current is not exactly 90 degrees, this is the magnetic field. This is the current carrying conductor, current. Now also the thumb shows the direction of force. Therefore, you can adapt this principle here. Four fingers show the direction of magnetic field. You can just see here. And current is going in this direction. You can just see. I told you here. Here the current is coming vertically down and it's going little bit away. Slant, but this is the direction of the magnetic field. So magnetic field direction. This is the current direction. Then the thumb shows the direction of force. Therefore, force will be vertically down, vertically down. Therefore, force on this part is towards you, force on this part is vertically down. This is the force direction, this is the force vertically down. Force on RS. Force on RS. What is the force on RS? Same as that of PQ. Same as that of PQ because all terms are same. Number of turns are there. N, magnetic field. B, current. I, length. L, everything same. Angle. Here the current is going vertically up and this is to the right. Angle is 90 degree. So sin 90, 1. Sin 90, 1. So same. Direction. Fleming's left hand rule. Four fingers show the direction of magnetic field. Four fingers show the direction of magnetic field. Middle finger show the direction of current because current is upward. See, without, I am not changing this picture. First one always you fix. Four fingers show the direction of magnetic field. This finger you should not alter later. Fix. Middle finger show the direction of current. See, current is up. Therefore, I have to bring it up. So, this is how I am doing. Now you stretch the thumb. Thumb will be inwards. See, thumb will be inwards. So, this is thumb. Inwards. Therefore, two side, two force, you understood? This is one force. This is another force. You can just see the two forces like this. Slant I can see here. Let's see, these are the two forces. One force will be outside, another force will be inside. These are the two forces. Downward force vertically down. Now the last one is SP, force on SP. Force on SP. It is same as that of QR. It is same as that of QR. So how much? N, B, I, B, sine. What is sine? It is sine 180 minus alpha. Because this is the direction of the magnetic field and the current is coming down. Therefore this angle is 180 minus alpha, but sine 180 minus alpha is sine alpha. Sine 180 minus alpha is sine alpha. Therefore it is same as sine alpha. Direction. 4 fingers show the direction of magnetic fields here. Magnetic field is to the right, I told first only. And current carrying conductor is lands here. This is how the current is coming in the lower part. Sorry, upper part. Not lower part, upper part. This is how the current is coming. Perfect, no? So what is the direction of force? Force will be, so here the current is coming like this, here away, here up, here, correct, no? So this is the direction. So what is the direction of force? Force will be upwards. So 4 forces are acting on the coil. Force acting on this vertically down, towards you, up, away. Now you see the 2 forces which are acting on the upper and the lower parts. See it carefully. One force is here. Another force is here. The 2 forces which are one vertically up, another vertically down, and both of them are equal. NBIB sin B alpha, NBIB sin alpha. They are equal, opposite, and acting in the same line. See here, same continuation of the line. There were 2 forces which are equal, which are opposite, and acting on the same line, they get cancelled. Therefore, upper force and the lower force gets cancelled. But what about these 2 forces? Sideward force. They are also equal. NBIL, NBIL. They are equal. See here, one is towards you. One is away from you. They are also equal. They are opposite, but they are not on the same line. One is pushing that side, another is pushing this side. See, this is the coil. Somebody is pushing front, somebody is pushing back. Then what happens? The coil will turn and come and stand from here. Why? From here it won't move. Why? Because when it comes here, now they also becomes equal, opposite, and on the same line. Now they are not on the same line here. In this position, they are not on the same line. When they are in this position, they are not on the same line. But when they turn, now they come to same line. Therefore, if the coil is kept like this, the coil experiences a torque and turn and come and stand here. Therefore, torque will act. Therefore, upper force and the lower force, they are equal and opposite gets cancelled. Whereas the 2 sideward forces, force on PQ, force on RS, they are equal, they are opposite, but they are acting parallel. 2 forces which are equal, opposite, parallel, and that is called couple. That's called what? Couple. What the couple do? Couple gives a pure rotatory motion to a body. Pure rotatory motion means it turns from there only. There is no translatory motion. If the coil is here, from there only it will turn and come and stand like this. Come and stand till the angle between the magnetic field and the coil becomes 90 degrees. Is it right? And what is the effect of this couple? The rotatory effect of the couple. We call it as moment of the couple. Rotatory effect of the couple, or we call it as moment of the couple, or in a simple word you call it as torque. Moment of the couple or torque. Rotatory effect of the couple. It is called torque. It is given by the formula tau is equal to force into perpendicular distance. Force into perpendicular distance. How to show now? How to find out the perpendicular distance? Tau is equal to, what is the force here? Force is NBIL. NBIL into perpendicular distance. Perpendicular distance, if you want to represent little bit three-dimensional idea, I'll just rub it here, top parts. There is no place here. Some part I'll just rub. Listen carefully. This is one force. This is another force. Clearly you can see, no? And this force, it is slant, not, it is not perpendicular, it is somewhere like this. This one I will represent in the blackboards here like this. This is how it is represented in the blackboards. Yes, yeah. Actually, they are like this, but it is shown in the blackboard like this. So, this is a part of the coil. One force away, another force towards. And this is the direction of the magnetic field. And this is angle alpha. And which is this? This is this length, and that is what? Breadth B. It is breadth B. So two forces. This is one force which pulls the coil away. Another force which pulls the coil towards you. So coil turns. And which is the perpendicular distance? Perpendicular distance is, this is the perpendicular distance. I call it as x. Perpendicular distance is x. So NBIL into x. Is it right? Therefore, two forces which are equal, opposite but parallel constitute a couple, and couple give pure rotatory motion to the coil. So coil turns, and the torque, the moment of the couple, is given by the formula any one of the force, because both forces are equal, into perpendicular distance. This is alpha, therefore this angle also alpha, alternate angle. From this triangle, what is cos alpha? Cos alpha. Cos alpha is adjacent side by hypotenuse. Adjacent side by, this is also alpha, you can see here alpha. Adjacent side by hypotenuse. Adjacent side is x, hypotenuse is b. Therefore, x is equal to b cos alpha. X is equal to b cos alpha. Therefore, tau is equal to n b I into b cos alpha. What is L into B? L into B, L is the length and B is the breadth of the coil, L into B is area. So tau is equal to N B I A into cos alpha. Now let's just make a small change. Let the angle between magnetic field and normal to the coil. This is a magnetic field. This is a coil. What is the angle between magnetic field and the coil? In this position, 90 degree. In this position, 0. But if you are calculating the angle between magnetic field and normal to the coil. Normal to the coil means this is magnetic field. This is normal. So in this position it is 90 degree. In this position it is 0. And that I take it as theta. So what is theta here? Angle between magnetic field and normal to the coil. Or we can say area vector. Area vector is always perpendicular to the area. So angle between magnetic field and area vector, let it be theta. So convert from alpha to theta. What I can write? Tau is equal to N B I A, shifting from alpha to theta. This is cos alpha. Cos alpha can be written as 90 minus theta, because this total angle is 90 degree. Out of that, this is theta. Then what is alpha? Alpha is 90 minus theta. What is cos 90 minus theta? Cos 90 minus theta is sin theta. So tau is equal to NBIA into sin theta. I think in the previous derivation we told a current carrying coil act like a magnetic dipole. An electron revolving around the nucleus. An electron revolving around the nucleus act like a magnetic dipole. When the electron is revolving like this, anti-clockwise, then the current will be clockwise. For the observer it is different. If I show anti-clockwise, for you it looks like clockwise. If I show anti-clockwise, for you it looks clockwise. If I show clockwise, for you anti-clockwise. So no confusion about that. So when the current is going in a circular path, one side act like a south pole, another side act like a north pole. It act like a magnetic dipole. Just like we have electric dipole, two equal and opposite charge separated by some distance. It is called electric dipole, and it is measured the electric dipole moment using the formula any one of the charge and dipole length. Similarly, in magnet also we have magnetic dipole. Normal magnetic dipole means an actual magnet. There are north pole and south pole, which is the real magnetic dipole. All the magnets are magnetic dipoles. Similarly, a current carrying coil can be also treated as a magnetic dipole. Because when a current is going in a coil, one side of the coil act like south and the side of the coil act like north. Where the current goes clockwise, that side is always south. For example, if I say the current is going like this, for me this is clockwise, for me it is clockwise, my side is south, but for you it is anti-clockwise, it is north. So current carrying coil act like a magnetic dipole, and the magnetic dipole moment is given by the formula product of the current into area of the current coil, current loop, into N is a number of turns. Therefore N into I into A, what is I? Current flowing in the coil, A, area of the coil, and N, number of turns. Therefore N into I into A, it is called M. What is M? M is called magnetic dipole moment. Magnetic dipole moment. This formula is just analogous to what you have studied in electrostatics. In electrostatics, we have studied that an electric dipole kept in electric field experiences torque. An electric dipole kept in electric field experiences torque, and that tau is equal to Pe sin theta. Remember? Tau is equal to Pe sin theta. This is same as analogous to that. This is the current carrying coil. Current carrying coil is a magnetic dipole, because one side act like north pole, another side act like south pole. A magnetic dipole kept in the magnetic field. Electric dipole kept in the electric field experiences torque. Similarly, magnetic dipole kept in the magnetic field also experiences torque, and the tau is equal to mb sin theta. What is P? Electric dipole moment. What is M? Magnetic dipole moment. What is E? Electric field. What is B? Magnetic field. What is theta? Angle between P and E. What is theta? Angle between M and B. Theta is the angle between M and B. Is correct? Theta is the angle between M and B. B is a magnetic field, and what is M? M is a magnetic dipole moment. Direction of the magnetic dipole moment is always perpendicular to the area. It is from south to north pole. If there is a circular coil like this, the magnetic dipole moment is perpendicular to that. That is why I took the perpendicular angle. So this is the direction of what? This is the direction of vector M. This is B. That is why the first formula we wrote tau is equal to P cross E. Similarly, second one we can write tau is equal to M cross B. Our current carrying coil, current carrying rectangular coil, which is also called magnetic dipole. When it is kept in the magnetic field, it experiences a torque, and the torque is given by the formula tau is equal to mb sin theta, where what is m? Magnetic dipole moment, b magnetic field, and theta is the angle between magnetic field and the magnetic dipole moment. Or we can say angle between magnetic field and perpendicular to the coil. Angle between perpendicular to the coil. Therefore, if this is the coil and this is the magnetic field, now theta is 0. Theta is 0. And there is no torque, coil will remain there only. If this is the magnetic field, if this is the coil, now theta is equal to 90 degree. The torque is highest and the coil will turn and turn and turn and turn and turn and come and stand like this. Why it will come and stand here? If you keep the coil like this, it will turn and come and stand here. Why? Because in this position, theta 90 degree, torque maximum. Torque decrease, 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 decrease. In this position, torque is 0 because theta 0. Is it right? Therefore, current carrying rectangular coil kept in the magnetic field experiences a torque, and the torque is given by the formula tau is equal to mb sin theta. Understood? Thank you.